My name is Ivo Eilers and I'm a Key Account Manager at SVS-Vistek. Today I will talk about advances in SWIR and UV technologies that open the door to new applications. SVS-Vistek is a German camera provider headquartered in Gilching, close to Munich. We have offices in Yokohama in Japan as well as in Louisville in Texas in the United States. Additionally, we have distribution partners all over the world. SVS-Vistek, which includes products from the Microtron brand, is part of the TKH Vision Group, which consists of unique machine vision players which cover a broad range of products. We offer a broad portfolio of industrial cameras with 2D area scan solutions with resolutions from about 1 megapixel up to 150 megapixels in 4 different series. Our interface options include GigE, USB 3, Camera Link, Coax Express 6 and 12, as well as 10 GigE, thus also offering high-performance interfaces for high data rate transmissions. With the Microtron brand, we offer high-speed cameras, optimized vision PCs, as well as recording cameras and systems. Additionally, we have solutions for polarization imaging in the SWIR as well as the UV spectral range. The latter are being covered in the talk today. For all our cameras, we provide tested and optimized machine vision equipment like optics, frame grabbers, and cables. First, I would like to briefly introduce the ultraviolet and shortwave infrared wavelengths regimes. A wide range of the electromagnetic spectrum from gamma rays to radio waves is shown here. The visible light that we humans can perceive covers only a small range from 400 to about 750 nanometers. The UV band is blue shifted relative to the visible light and can be divided into far UV, mid UV, which starts at about 200 nanometers, and near UV. Redshifted from visible light is the near infrared and the SWIR waveband range, which starts at about 1 micrometer and extends to about 3 micrometers. Today, I want to show you that you can image wavelengths in both the visible and SWIR spectral regions using a new sensor technology called SWIR. Why is this of interest? Well, with wavelengths ranges outside of the visible range, you can detect object characteristics that are invisible in the visible spectral range. This in turn opens the door to new machine vision applications. SWIR is a sensor technology developed by Sony for broadband and high-sensitivity SWIR imaging. It is an indium-gallium arsenide-based sensor that enables finer pixel pitch while maintaining high image quality. To stack the readout circuit to the pixel chip, Sony used copper-copper connections instead of the widely used bump connections shown schematically in the right image. This results in a reduction of the pixel size from typically 10 micrometers or more to a small pixel pitch of 5 micrometers. This allows the production of compact sensors with less material usage, which results in attractive price points for an indium-gallium arsenide sensor while maintaining high image quality. In addition, Sony has succeeded in reducing the thickness of the topmost indium phosphide layer. This layer absorbs visible light. By reducing its thickness, the underlying indium-gallium arsenide layer sees visible as well as SWIR wavelength. As a result, the sensor offers high quantum efficiency for both the visible and SWIR spectral regions as shown in this graph. This allows imaging of wavelengths from 400 nanometer to 1700 nanometers with a single camera, which can reduce the complexity of machine vision systems, especially for applications where visible and SWIR light are used. At SVS-Vistek, we have integrated the new Sony SWIR sensor into both our EXO and FXO series to provide SWIR imaging with the benefits of an optimized machine vision camera. We offer cameras with resolutions from 0.3 megapixel up to 1.3 megapixel, which is relatively high in the SWIR wavelength range. As mentioned, a small pixel pitch of 5 micrometer is realized, which allows compact sensors. In addition, we provide a choice of interface options. With Gigabit Ethernet, our 0.3 megapixel version allows 260 frames per second and the 1.3 megapixel version 94 frames per second. If you prefer Coax Express 12, you get up to 134 frames per second with the 1.3 megapixel version. The global shutter sensor allows imaging under dynamically changing conditions without inducing image distortions. Despite all the optimizations, the manufacturing of the indium gallium arsenide sensor is prone to some defects that can manifest themselves in defective pixels or image inhomogeneities. To optimize image quality, we incorporated a non-uniformity and defect pixel correction algorithm into our camera. 8 and 12-bit imaging is provided with a dynamic range of approximately 59 dB. Our cameras provide access to features and functionalities of an industrial-grade camera, including built-in lighting control, among others. Finally, a strong thermomechanical design enables effective heat transfer of the sensor to the outer shell of the camera. Especially when the camera is attached to metal, effective passive cooling of the sensor can be achieved. To illustrate some application areas, I would like to show you some use case examples. One application is the detection of water, or more generally moisture. If you look at the absorption of water as a function of the wavelength, one can see that water has a prominent absorption band at around 1450 nanometer. This property can be used to visualize water that is difficult to detect in the visible spectrum. In this image, you see a sponge and a shoe sole in the visible spectral range. The presence or absence of water is not evident in this image. However, if we switch to the SWIR spectral range using 1450 nanometer light, we can clearly see the areas of the object where moisture is present. Another application where the same concept is used is in the food industry, for example, in the inspection of apples. Some apples may have internal defects, such as bruises, that are difficult to detect with visible light. However, as soon as we switch to the correct wavelengths, the bruises become clearly visible, as can be seen in the image on the right, which was taken at 1450 nanometer. Moisture or water detection is not the only application example in the food industry. Other materials that have almost the same color in the visible spectrum can have different reflectivity in the SWIR range. In this example, you see black beans, metal, stones, and plastic all mixed. In the visible range, these materials are difficult to distinguish from each other. If we look at the same scene in the SWIR range, in this case at 1300 nanometers, we see that the beans show a strong reflection so that they appear white and can be clearly separated from the other materials. With SWIR at 1550 nanometers, a content inspection of plastic containers is rendered possible, which is not so easy in the visible regime. And finally, another important area of application is found in the semiconductor industry. Some plastics have the nice property of becoming transparent in the SWIR spectrum. Silicon also has the property of becoming transparent in the SWIR range. This is a reason why it is not possible to use classical CMOS sensors to detect SWIR wavelengths. In the image on the right, taken at 1550 nanometers, one can see through the wafer. This allows the detection of defects inside of the wafer before further complex and costly processing of the wafer. In addition to advances in SWIR imaging technology, progress has also been made in the ultraviolet spectral range. With a new sensor technology, also developed by Sony, it is now possible to image wavelengths from 200 nanometer to over 800 nanometers with high resolution. In the visible range, light is very often detected by CMOS sensors. Here you see a side view of a classical CMOS sensor, which consists of photodiodes, microlenses, and in most cases a cover glass. There are some aspects that make classical CMOS sensors ineffective at detecting UV light. The photodiodes and the microlenses are usually not optimized for UV light, and the microlenses might even be damaged due to the higher photon energy in the UV light range. Another problem is that a normal sensor cover glass absorbs light under 400 nanometer. This results in a low transmission and low quantum efficiency in the UV wavelength range. Here you see an example of a CMOS quantum efficiency curve of a sensor from the Sony Pregios S sensor series. As you can see, the quantum efficiency is low in the UV range. Especially below 400 nanometers, the quantum efficiency rapidly drops and reaches values of 0 starting from about 300 nanometers. Therefore, we need to use especially optimized sensor technology in order to detect UV light. Recently, Sony launched such a new CMOS sensor that is optimized for UV detection. In this new sensor, the cover glass is replaced by a quartz glass, which has a much higher transmission in the UV range than normal glass. Thus, the transmission in the near and middle UV is higher than for normal glass. In addition, the sensor uses micro lenses and light-receiving pixel units that are optimized and adapted for UV light. As a result, we now get a CMOS sensor with a significantly increased quantum efficiency in the UV waveband. You can see that the quantum efficiency in the range of 200 to 400 nanometers is considerably higher. If we compare it to the normal Pregios S quantum efficiency, this becomes even clearer. Please note that the sensor also detects visible light. It can detect UV and visible light simultaneously if needed. This new technology allowed us to develop a new high-resolution and fast UV camera, which I would like to introduce to you now. We integrated the new Sony UV sensor in our FXO series. We did this to take full advantage of the high sensor speed that is supported by the high bandwidth of the FXO series. You get a high resolution of 8.1 megapixel, which to our knowledge is currently the highest resolution available for UV machine vision camera. Sony's new Pregios S technology is used to realize the pixel structure, resulting in a pixel pitch of 2.74 micrometer. We offer frame rates of 87 frames per second with 10 GigE or 1 times CXP12 and up to 194 frames per second with our high-speed 2 times CXP12 interface. Again, you get the benefits of a global shutter sensor. The image quality is very good and is comparable to the known high Sony quality of normal Pregios CMOS sensors. This includes the possibility of 8 and 12-bit readout, a signal-to-noise ratio of up to 40 dB, and a dynamic range of 70 dB. As previously presented, a rich feature set as well as an optimized thermomechanical design are available. Now I would like to show some application examples where the UV camera can be used. The first application is the sorting of materials. Here, the high frame rates of up to 194 frames per second are beneficial, as a high material throughput is typically given in sorting applications. The global shutter functionality ensures distortion-free imaging even for moving objects, which is an advantage in this application. An example is the sorting of different plastics. In this graph, you can see the transmission spectra of different plastics. As you can see, PMMA absorbs light in the UV range. So if we use an illumination wavelength of 365 nanometer, PMMA will absorb light strongly, while other plastics such as polystyrene will not. As you can see in this UV camera image taken at 365 nanometer, we can clearly distinguish PMMA from polystyrene. In the visible waveband range, this separation would not be feasible. Another example is the separation of glass and plexiglass. Here you see both glass and plexiglass pieces mixed together. With visible light, it is difficult to separate the two compounds. However, when UV light is used, here at 365 nanometer, separation is easy. In addition, the UV camera can be used for the inspection of infrastructures. In our example, specifically for the inspection of power grids and overhead lines. Overhead transmission lines use strain insulators to prevent the power lines to be in touch with the ground. Too much electrical stress can break down the insulator. Simply put, in that case, electrical discharges occur from the power line through the body of the insulator. With the UV camera, it is possible to detect electrical discharge. Here you see the same field of view in the UV waveband, where discharge events are clearly visible. In the superposition of the visible and the UV image, a localization of the discharge events is possible. UV cameras are also used in the semiconductor manufacturing industry. Application areas include the surface inspection of unpatterned wafers that look for polish marks, crystalline pits, voids, or other defects that can affect the performance of integrated circuits created on those wafers. UV light tends to scatter more intensely from the surface and has shorter penetration depth than longer wavelengths, which makes it a great choice for surface inspection. Another big reason to use UV light is its resolving power as described by the diffraction limit of light. The diffraction limit d is the overall limit of the smallest details you can resolve with an optical system. As you can see from the formula, the diffraction limit has a linear dependence with the wavelength lambda. UV light, with its shorter wavelengths than visible light, allows to resolve smaller structures than visible light. PCBs must be protected in some form against the environment. This is achieved by suitable coatings or protective resins that protects the PCB from moisture, vibration, mechanical or thermal shocks. Without protection, burn-throughs or electrical bypasses can occur in the PCB. These protective resins are typically transparent to visible light, but often show strong absorption in the UV range. Therefore, UV cameras can be used to ensure proper application of the protective coating. Here you can see an example recorded with visible and UV light of a sample that we treated with a protective resin at SVS-Vistek. As you can see, the UV band clearly shows that some parts of the PCB have not been properly treated, which is not visible in the visible wavelength range. This was what I wanted to present you today. Thank you very much for your attention. This concludes my talk.